We've gone over this. But what this all boils down to is biogeochemical cycling. And a lot of researchers will claim that they are biogeochemists. What is important to realize is that some people are biogeochemists and some people are biogeochemists, and they all have their specialities within, but it is supposed to be a blend of biology, geology, and chemistry, because you can't understand in an environment one without the other. Life alters rocks. Rocks inhibit where life is, and rocks and life are all associated with chemistry. So the three of them tie in nice and neatly. And what we're going to go through now is some cycling and cycle just means going around in a circle, of different elements, different molecules that we have talked about, but we're going to talk a little bit less in terms of the individual organisms and more in terms of the chemistry and what's going on chemically through these different pathways. The main ones that we will talk about are located on the side here of this figure. Carbon, nitrogen, sulfur, iron, phosphorus, and manganese are the ones that are the most reactive, most involved within the environment. The noticeably absent one on here is oxygen. They probably should have included that one on there, but oxygen is usually seen as an add-on to a lot of the other groups, but you do have, as we well know, aerobic respiration, which does cycle oxygen through an organism in a way that's not biologically, it's not anabolic, but it's catabolic, which we know what that is now. This is a good table to go back and check yourself on if you know the different reduction points, who's going where, oxidized form, reduced form. You can draw lines between these. I'm going to show you some circles to put it all in better context. Use this as a good study guide at the tail end. I promise it will help. Now this is something that's not in your book. Something this will be. When we're talking about reduced and oxidized forms, and we're talking about this, you see the charges, -4, so let's say the carbon here, -4 here on this side, +4 on this side. Nitrogen, -3 to +5. Sulfur, -2 to +6. What we're talking about on that is electrons, and we're talking about valence. We're talking about charges. We're talking about either the loss or gain of electrons. Now, movement of electrons, where have we talked about that before? Electron transport chain through chemistry, everything, exactly. This is what is either donating an electron, so they're already negative, and if you donate electrons, you get more positive, or you accept electrons, you're positive, and you get more negative because electrons are negative, so the more you accept, the more negative you are, the more you donate, the more positive you are. So it's the movement between being negative and being positive, and all of this is involved in a thing called redox, or redox reactions. Oxidation, reduction, reactions, redox. This whole bit is the biological mechanism of becoming a battery, of moving electrons from one spot, positive source, or negative source rather, negative electrons leave the negative side and go to the positive side. Opposites attract, negative attracts positive, so, or positive attracts negative, and the electrons get dumped off onto this other side. It's the movement of electrons. The redox reaction here, oxidation reaction, there's a reducing agent, it now becomes oxidized, oxidizing agent becomes reduced, the electron is donated from this side and it is accepted by this side. This is your electron donor, this is your electron acceptor. It's the movement of those electrons, it's the movement of the electrons that act just like your power cord on the wall, your battery in your computer. It's moving electrons, and while the electrons are moving, work is being done. This is stuff that we've talked about before. Now you have some more slides on it. You see the oxidation side. Yes.
So are they using the wrong terms there? Or is this organic heterotrophs the back? Or there?
Here?
Yeah. What about, like, if it says organic hetero, it should be organotroph, and then inorganic should be lithotroph, shouldn't it?
Okay, I'm not getting into, okay, it can be. So organic is still a heterotroph.
Well, I thought that means that's where it gets its carbon source from, not where it gets its electron source from.
It's, oh, I see what you're saying. You're going off only with the organic versus hetero, not that organic is wrong. Is that what you're saying?
Well, when it's like talking about hetero or autotroph, it's referring to like where it's getting its carbon from.
Oh, I see what you're saying. I see what you're saying.
Not where it's
So
getting
you're saying
its
litho
carbon.
versus organo.
Right,
Yeah,
it should be
technically,
organotroph, and then inorganic is lithotroph.
technically, yeah, I guess you could switch over. Yeah.
Don't autotrophs have to be lithotrophs?
No, you could have an auto heterotroph.
Mhm.
You could have a photoheterotroph.
Like purple.
Yeah, you could have a photoheterotroph
Okay.
because it's where they get their energy versus where they get their carbon. And the hetero is carbon. Yeah. So you're probably right. Yeah, vice versa. But oxidation side. But what we're talking about here more with the oxidation side is that oxidation side is the one that is getting more positive. It is donating an electron. So what's being the oxidized side is donating the electron, is the electron donor. The reduction side, this is the side that is getting more negative. This is where we now start talking about and where we characterize this whole respiration structure. All right, it's electron tower theory. This is from a good friend of mine, Bo Barker Jorgensen, who's over in Denmark now. The prototypical, if you're going to make a movie about a guy who looks like a grandfather Viking guy, this just would be Bo Barker here. This guy's great. He's like that tall, white beard. Disney. But the whole point of this, your book talks about this in a little bit of detail, but the whole point of it is, and what we've talked about before, is that you don't get the same amount of energy with different either electron acceptors or electron donors. So no, let's say that different. Let me say that differently. You get different amounts of energy with different electron donors and electron acceptors. It depends on what you pair them up with. This oxidation reduction reaction, the two sides, oxidation side and the reduction side, two half reactions. And we said before that they have to be separated because if they're separated, now you can flow an electron from one side to the other, and while you're flowing, now you get to do something. You have power, you have energy, you can do some work. And so these two half reactions, the oxidation reaction, where the electron is donated, to where it's being accepted, the electron accepted, the reduction reaction are separated out. What you see here is the second half of it, the terminal electron accepting process. That last bit. In that last bit, this is where the electron's being dumped. What we're seeing here is we have an organotroph. We have organic matter being used as the electron donor. This electron donor is losing that electron through the electron transport chain. It's being shuttled off to either oxygen, nitrate, iron and manganese, sulfate, carbon dioxide, or a fermentation process, CO2 to CO2. But each one of these gets an electron. The higher you're up on this tower, the more energy you get, the more bang for your buck. So if you are aerobic, oxygen is your terminal electron acceptor, you get the most energy. If there's no oxygen around or you can't use oxygen, you'll default to nitrate. That gives you the second most amount of energy. Iron and manganese is third, sulfate is fourth, carbon dioxide is at the tail end. Which means that if you feed a group of microorganisms, a group of organisms that we have just now covered, each one of those different taxonomic lineages, if you feed them the same amount of organic carbon, those that are aerobes will use it first, then nitrate, then iron, and down the line. And so what that looks like is this. Within an environment, you then get stratification. You get those organisms that are capable of O2 respiration will be at the very top. So that nice juicy candy bar that falls on that salt marsh, the first bugs that are going to destroy it are the aerobes. And they're going to use that carbon until either the carbon's gone, they've eaten the whole candy bar is not there anymore, they have nothing left to eat, or they have nothing left to breathe, they have no more oxygen. If they run out of O2, they can't breathe. Aerobes are now toast. So let's say that the candy bar was so big, you run out of oxygen. They've literally eaten themselves out of oxygen. Now, the nitrate producers kick it in.
and say, great, good, get out of my way. I can breathe nitrogen, I can breathe nitrate, sorry, get the molecule right. I can breathe nitrate. I get the most energy, so I can outcompete everybody else beneath me. I'm gonna breathe nitrate, and I'm gonna now eat the candy bar. We run out of nitrate. Now, the iron reducers, the manganese reducers, the metal reducers kick in. When they're out of oxidized metals, because remember they're reducing the metals from an oxidized state to a reduced state, reduction, reaction. When the metals are gone, now it's sulfate. When sulfate's gone, now it kicks over to methanogenesis, CO2 reduction to methane. One of the misnomers that is propagated through biology a lot is that we breathe in oxygen and we breathe out CO2. That's right? Everybody knows that, right? You breathe in oxygen, you breathe out CO2. Is the oxygen that you breathe in the same oxygen that's on CO2? Correct. No, it's not the same. Just because it's oxygen, just because it's an O2, it's not the same O2. It's not the same oxygen molecule. The oxygen you breathe in is reduced, well, you see here, is reduced to water. What you breathe out is what you breathe out is CO2 that's coming off of the organic matter. Because remember TCA cycle, remember glycolysis. Remember what happened with glycolysis in the TCA cycle is that you kicked off CO2s. As the electrons were donated, as that organic molecule was broken down, you mineralized carbon. You made carbon into CO2. That's the CO2 that's coming out. It's off the electron donating process. The water is produced, the oxygen is reduced and forms water. So it's not the same. All right? You see that? Got that? Good? Clear as mud? All right. All right, so, and the reason for this was actually a sample that we took out of St. George Island in Florida. And we did this just to show that, and we did the full molecular analysis of this, we did a community characterization of this, and you can see those microbes that fit along with this table